Segments 42 and 43, Neutron stars, black holes, and general relativity. When electron degeneracy pressure is not sufficient to support a core, as in the case of the iron core in the middle of a massive star, it collapses further and a neutron star forms, or in extreme cases even a black hole. The neutron star formation, where you break apart the iron nuclei and convert the protons into neutrons, releases copious amounts of neutrinos. And as I mentioned in the last segment, the Kamiokande neutrino detector saw the burst from supernova 1987A, confirming this idea about how supernova explosions unfold and how this leads to the formation of a neutron star. The neutron stars were first discovered as a result of observing what are called pulsars in the middle of supernova remnants, like the Crab Nebula that we saw in the last segment. We can tell that these objects are there because they're rotating extremely rapidly and they have enormous magnetic fields that generate radio waves that are quite powerful. But there actually are three possibilities of what's left over after a supernova explosion. In some cases, the explosion completely destroys the star, and there's no remnant left whatsoever. In others, a neutron star forms, this dense ball of neutrons that's only a few miles across. And in some cases, that neutron star is so massive that even the neutron degeneracy pressure is not enough to support it against further collapse, at which point it collapses to become a black hole. We can look at some of the properties of black holes in a very simple way, which is to look at the issue of how much energy a particle would have if it's just at the point of just not escaping, so at the boundary between being able to escape from a gravitational field and not escape. So you can set the kinetic energy of a particle, which is 1/2 mv squared, equal to the gravitational potential energy, gmm over r. And if you use the escape velocity and cancel out the mass of the test particle on both sides, you have 1/2 v escape squared is equal to gm over r. And if you do a few algebraic conversions, you can set that escape velocity equal to 2 gm over r to the 1/2 power. Now the maximum escape velocity anything can have is the speed of light. So we can solve this equation for the radius at which the escape velocity equals the speed of light. And that radius, which is known as the Schwarzschild radius, is equal to 2 gm over c squared. So it comes from this very basic derivation. And in numbers, that radius is about 3 kilometers per solar mass. That is, a 1 solar mass black hole would have a radius of 3 kilometers, and a 10 solar mass black hole would have a radius of 30 kilometers. So it scales with mass larger and larger, but it's very, very small. So here we have an illustration in miles, but close enough. A white dwarf is maybe 10,000 miles across, about the size of the Earth. A neutron star is about 10 miles across, about the size of Austin, and a black hole is about 3 miles across, a size of the neighborhood between here and the lake. So gravity can be looked at in a number of ways, and the strength of gravity, the force is minus gmm over r squared. But general relativity provides a different description. Massive objects actually curve space and time, and objects move in this curved fabric of space-time. So we don't think of it just as a force between objects, but an actual changing in the shape of space. A black hole is something where the gravitational field is so strong that not even light can escape. It's a singularity in space-time where things are bent completely. And the event horizon is the first point at which light cannot escape, and that's given by the Schwarzschild radius. The Schwarzschild radius is that distance to the point where light can't escape anymore. Inside of that, all mass falls in to this infinite density singularity at the center of the black hole. But if you ask yourself the question, what difference does it make outside the black hole? The answer is, until you get very close to it, very, very little. And the external properties of a black hole relate mostly to the fact that you can get very far down into this gravitational potential before you hit anything significant. If you ask, What would happen if I replace the sun instantaneously with a black hole? The answer is very simple. It would get dark, because the Earth would continue to orbit around this one solar mass black hole just as it orbits around the sun, but it wouldn't be shining anymore. The way we wind up seeing black holes is twofold. One is by their effects on gas around them. In the left-hand illustration, you see a cartoon of a binary pair where a star is losing some of its outer envelope onto an accretion disk around a black hole. The material doesn't fall directly into the black hole because it has some angular momentum. It falls down and hits this disk, gets very close to the black hole, heats up the disk, and that heating up makes the disk shine very brightly in X-rays, and we see that X-ray emission. And on the right hand, you see a set of orbits observed for objects moving around the center of our galaxy, which contains a black hole with several million times the mass of the sun. And by looking at the shapes and sizes of these orbits and the speed at which things move around them, we can derive that estimate of the mass of the black hole, and we can demonstrate that all that mass is concentrated in a very, very small space. Now, what would happen if you fell into a black hole? Here's a typical victim, and if you fell into a black hole, a number of things would happen. The tidal forces, because you can get so close to the object and you're finite in size, would stretch you apart as you went in, plus some relativistic effects would leave you moving closer and closer into the black hole as seen from the outside, although you would fall in very quickly. As we looked at you, some of the relativistic effects would make it look as if you were taking an infinitely long time to fall in there, longer than to the end of this course, in fact. Now, there's an easy way to look at the behavior of objects in the presence of a strong gravitational field that comes from a point that Einstein made called the Equivalence Principle. This is a very theoretical argument that underlies all of general relativity, but it turns out that this general relativistic argument is important even in our everyday lives, because GPS satellites and the GPS in your phone would not work unless we made corrections for general relativity that are based on this principle. And what Einstein said is that the mass, the inertial mass, that is the property of mass that resists force, that comes into Newton's second law, F equals ma, is the same fundamentally as the gravitational mass, the mass that makes things attract each other, that makes you fall towards the center of the Earth. That's the m in F equals gmm over r squared. He's saying that these two masses are fundamentally the same. Now, we intuitively know this, but he said, let's make this an absolute principle and follow the consequences of this. One consequence of it is that it should not be possible to tell the difference experimentally between life in a zero-gravity accelerating frame, that is someplace far away from any mass but powered by rockets to accelerate at some acceleration, and life in a frame where the gravitational acceleration is equivalent. So let's make this a little more concrete and look at elevators. So I call this the Aufzugsgedankenexperiment. So a Gedankenexperiment is a thought experiment, and an Aufzug is an elevator. And what Einstein said was that there's no experiment you can do inside an elevator that's standing still waiting on the 14th floor of R.L. Moore Hall, and an elevator that's being blasted by rockets into space and accelerating at 9.8 meters per second, the same as the acceleration of gravity on the surface of the Earth. So let's look at a few examples here. In our stationary elevator, if we shine light sideways, in our rocketing elevator, if we shine light sideways, one of the consequences is the bending of light. It takes a finite amount of time for the light to travel across the elevator, and we see clearly in the accelerating case that by the time the light gets to the other side of the elevator will be moving at a different speed than the flashlight is moving, and so a slightly lower point on the elevator will be the target when the light hits it. And this appears to the man inside the elevator that the light path is curving. And Einstein's Ansatz, Einstein's supposition, says that then we must see the same thing in a gravitational field. And we've verified this experimentally. It really is true. If you shine the light up, same thing. The two have to be the same. But in the accelerating frame in the rocket, by the time the light gets to the top, the elevator is now moving at a higher speed, and so the light has to go from that frame into the new frame and a little bit farther. It's now coming from a source that's moving a little bit slower, and so the light will be slightly redshifted as you move up in the field. People have actually tested this in skyscrapers with very, very exquisitely precise instrumentation and demonstrated that this gravitational redshift effect does exist. So both of these have been proven by experiment, and they're fundamentally underlying general relativity, which is the theory that we use to understand black holes and the phenomena around very compact objects.